Greetings everyone, this is Riya Khan and I will be presenting our paper Enhancing Cephalometric Landmark Detection with a two-stage cascaded CNN on multi-resolution multimodal data done with the collaboration of MIUA Lab at the National University of Sciences and Technology, Pakistan and RIFA International University, Pakistan. To firstly introduce the topic, cephalograms are lateral X-rays of the human face used by orthodontists to perform cephalometric analysis. In this analysis, landmarks are marked on the cephalograms and vectors and angles between these landmarks are measured. Cephalometric analysis is primarily used as a treatment planning tool by the orthodontists. However, marking these landmarks and finding these measurements is a tedious and time-consuming process for the orthodontists. Also, it is prone to high intra-observer and intra-observer variability. Therefore, there is a need to develop an automatic system that can identify these landmarks accurately, consistently, and rapidly. To measure the efficacy of any such system, two evaluation metrics are predominantly used: mean radial error (MRE) and the success detection rate (SDR) at different ranges, keeping in mind that 2 mm is the clinically acceptable range. However, developing such a system faces two major challenges. Firstly, when a 3D skull is projected to a 2D cephalogram, it gets hard to distinguish overlapping structures. Secondly, the publicly available dataset for cephalometric landmark detection are very small, proving it challenging to develop generalized models. The state-of-the-art dataset is the ISB 2015 dataset, which contains only 400 cephalograms with 19 landmarks annotated per image, captured from a single imaging device, reducing the resolution variation of the dataset. The prediction methods proposed in the literature using this dataset can be divided into coordinate regression and heat map regression. And the literature has utilized many approaches, including single-stage CNN, multi-stage cascaded CNN, transformers, and even graph convolution network. However, despite using such latest and novel techniques, a generalized model cannot be proposed while using a limited dataset as ISB 2015, limiting effectiveness on cephalograms from diverse sources with varying resolutions and spatial dimensions. Therefore, to identify the research gaps, they can be divided into three. Firstly, there are generalization challenges. Secondly, there's a need to develop models that can be applied to cephalograms of varied resolution and spatial dimensions. And thirdly, the datasets available are small and less diverse. Therefore, we propose to utilize the RS dataset. It was proposed in 2023 at the Cepha 29 challenge and is a promising dataset with high variations. And thus, there's a need to develop models utilizing this dataset. We propose a two-stage novel framework that combines scale-invariant ROI detection with accurate landmark regression. The RS dataset contains a total of 1,000 cephalograms, which is more than twice of ISB 2015 dataset. The cephalograms are captured from 7 imaging devices with 5 resolution variations. This proves that this dataset is highly generic and can be used to develop generalized models that are more clinically relevant. The number of landmarks annotated per image in the RS dataset is also 29, which is 10 more than the 19 landmarks annotated in the ISB dataset. These landmarks are annotated by a team of 6 expert orthodontists. When further analyzing the dataset, we encountered a few challenges and tailored our methodology accordingly. Firstly, cephalograms naturally have a huge spatial dimension, and it can be challenging to use the cephalograms at their original dimensions, as this can lead to more memory and computation-intensive models. A natural solution to this is to resize the cephalograms to a fixed dimension. However, since the RS dataset cephalograms come from varied imaging devices, there is a variation in the spatial dimension, and resizing can lead to bony structure deformation. For example, if we resize a horizontally oriented cephalogram, as in B, to a vertically oriented spatial dimension, as shown in C. Lastly, some of the cephalograms contain excess black pixels as shown in the image D at the edges, which is excess information being fed into the network. The solution we propose to solve all these challenges is to use a two-stage cascaded CNN approach, where the first stage trains the network that extracts the craniofacial region from the cephalogram. This craniofacial region can then be resized to a fixed smaller dimension without distorting the bony structure. Therefore, in our proposed methodology, first the cephalogram at its original dimensions is fed into the craniofacial region detection network that regresses the craniofacial region. This is then cropped and resized and then fed into the cephalometric landmark regression module that regresses all of the landmarks at once. To look further into the craniofacial region detection network, we use the first three convolution blocks of BGG16 to predict the top left corner coordinates along with the height and width of the bounding box containing the craniofacial region. The ground truth bounding box is identified by adding a margin of 128 pixel padding to the minimum and maximum landmark coordinate. This module makes our proposed approach input spectrogram resolution invariant. The second stage of the proposed method is to regress the landmark locations using the cephalometric landmark regression module. This stage regresses all landmarks simultaneously employing a feature pyramid network with heat map regression. The FPN introduces multiscalarity to our network, allowing for landmarks with varied discriminative features to be identified correctly. The ground truth heat maps are produced using Gaussian distribution. To move on to the results, this slide shows the results of the craniofacial region detection module. The evaluation metric used is intersection over union IOU, and our proposed model achieved an average IOU of 0.865. Secondly, this table shows the results of the cephalometric landmark regression module, which achieved an MRE of 1.789 on the RS test dataset with 78.44 SDR at 2 mm range, which is the clinically acceptable range. This figure shows 4 images with the predicted heat maps overlaid in the first row, with the second row marking the ground truth and the predicted landmark locations. Moving towards the discussion, we performed various ablation studies to reach our optimal method. For craniofacial region detection, we tested different bounding box configuration and found predicting the top left corner coordinates with height and width of the bounding box achieved optimal results. Also, 128 pixel padding achieved the highest IOU. Secondly, various backbones were also tested, and it was found that any backbone more complex than BGG16 quickly overfits. Among the various back convolution blocks of BGG16, using the first three convolution blocks achieves the best performance. For the cephalometric landmark regression module, we compared coordinate regression with heat map regression. The best performing model of coordinate regression was BGG16, while the best of heat map regression was FPN with BGG16 backbone, which also outperformed our coordinate regression BGG16 model, achieving an MRE of 1.789 with STR at 2 mm of 78.44%, making this our model of choice. Therefore, to conclude, we proposed a novel two-stage cascaded framework where the craniofacial region detection module extracts the craniofacial region ensuring scale and resolution invariance, while the cephalometric landmark regression module predicts the landmark locations, capturing global constraints and local features for accurate landmark detection. The model achieved an MRE of 1.789 with STR at 2 mm of 78.44%. Lastly, we acknowledge the support from the Islamic World Educational, Scientific and Cultural Organization (ISESCO) in establishing the ISESCO Chair of Data Science and Analytics for Business at the National University of Sciences and Technology (NUST). Thank you.